Okay, welcome to lesson 15. So we're going to talk about conditional events and independent events. So we're going to return to the example where we have those 10 students. A handful of them are pre-med students and some of them are international students. And we want to know if we had this example, what the chance that if we randomly selected a student that they're pre-med. So I'm going to go ahead and I'm just going to relabel everything. So M for pre-med, capital I for international, and then I'm going to put my, that S looks horrible, my sample space here. So there was 0.3 outside of the circles. Inside just this wedge was 0.2. Inside the overlap was 0.2. 0.3. So what is the chance of randomly selected student? So probability that I select the student. So first off, I need to think how many students am I picking from? There are 10, so that's what goes on the bottom. How many of those 10 are pre-med? So I count them up, 1, 2, 3, 4, 5. So 0.5. Or I like to put the 0, 50% chance that if I randomly select a student that they are a pre-med student. So this question is asking a little bit differently. It's asking us to not focus on all 10 students, but to actually be narrower. So suppose I randomly select a student, but we know that this student is pre-med. So if I look at just the pre-med students, and we'll go through this notation. So this is a vertical bar. Given I know that they're pre-med, what's the probability they are an international student? And we'll go over notation more. So number of meds or pre-med students. So I'm going to count them up. There are 5 of them. So if I take these 5, how many of those students are international? 1, 2. So 2 out of 5. So 0.40. Or 40% chance. So if I know that I randomly selected a student and I also know that they were a pre-med student, there's a 40% chance that I also selected a student that was international. So it's about shifting our perspective. The first one we said, hey, out of all 10, what's the probability I pick a pre-med? The second one saying, hey, let's say I know it's a pre-med student, what's the probability that it's also international? And the giveaway to this type of question is we're going to often have the word given. And we'll go through that as well. So conditional probability. So for any 2 events, so if we have events A and event B, the probability of event B can't be equal to 0 because we can't divide by 0. It'll make every single calculator unhappy. The conditional probability of A given B. So if you know B has happened, what's the probability A has also happened? That's what it's asking. So you can define it as the probability that both of them happen, so probability of A and B over just the probability of B. And for me, it's easy for me to say, oh, well, whatever's here goes here. And it's always both, the probability of both on top. So they redefine the sample space. So what it does is it narrows it down. So instead of looking at all 10 students in that sample, now we're only looking at the 5 students in the pre-med, like subsample. So a familiar example, we're back to the Pew Research Center looking at smartphones and broadband for Internet of U.S. adults. And now we can ask, so 77% of these adults have a smartphone, 65% access internet at home with broadband, 52% have both. So here's the question. Given someone accesses the internet with broadband, what is the probability that you've selected someone that also uses a smartphone? So for me, probability that they also use a smartphone given, so this is just a vertical bar, given that they have broadband. So I'm going to write this part out, but I'm going to throw in the Venn diagram because that would be useful here. So my Venn diagram, here's my sample space. S for smartphone, B, I'm going to have it overlap more. B for broadband. So 0.52 are in both. 0.25 are in smartphone but not in broadband. 0.13 are in broadband but not smartphone. And then 0.10 left over, have none of it. So the idea is if I say, hey, I know someone has broadband, what's the chance they also access the internet with a smartphone? So we're asking, how big of a portion is this part out of this whole thing? So here, the probability of both, that's 0.52. Out of this entire wedge, you have to add these two together, you get that 0.65. So this is not something math top of my head. I'm going to use a calculator. So I end up getting 0.8. I'm going to throw in a 0. This means that 80% of the US adults that have broadband also have a smartphone. And we're just focusing on this circle. So 52% makes up how much of 65%? Clearly, I definitely did not draw this to scale. Don't worry, I'm not quitting my day job anytime soon to become an architect. Promise. So one thing that can be super handy with this type of conditional probability are tree diagrams. So a tree diagram, this is going to look kind of funky. So suppose I have events A1, A2, and so on. K just represents it goes on to whatever point you want it to. And then I have a second set of events, B1, B2, all, and so on. So if I have 3 options that it could be, so maybe I have like a spinner and it has 3 colors on it. I could get color 1, color 2, or color 3, that kind of idea. I'm looking here. So then from here, B1, B2. So the probability of B happening given A1 happens. And then I can just fill out for the rest. This is a lot easier to see in context with a problem. So that is going to be our next step. So our general multiplication rule allows us to calculate the intersection. So if I want to say like, hey, what is the probability of a certain combination, you can actually go down the branches and go, oh, well, this probability times this probability kind of thing. So yes, here's this equation. Strongly recommend, like, definitely tune in for the next example. It's going to make a lot more sense with an example in context. So we have a video game example. The Pew, because apparently we just love using Pew research projects. They've found in a survey, and this might be outdated, especially since COVID, 67% of adults in the US play some kind of video game. 22% that do play video games say they call themselves a gamer. So draw a tree diagram. So for me, I'm going to ask, like, what was asked first? So play. So I'm going to say, V is plays video games. And then V complement doesn't play. And then, so we ask them if they play, so some people play, some people do not play. So the probability that they play, given this, is 0.67, so 67% play. So if 67% play, whatever's left over are the people who don't. So 1 minus 0.67, so 0.33. So I have 33% of say they don't play. And then from here, then we ask if they call themselves a gamer. So once again, G, I'm going to say they call themselves a gamer. G complement, not a gamer. So from here, a person who plays video games could be a gamer, or could call themselves a gamer, and that happens 0.22 or 22% of the time, which means that of people that play video games, we still have 78%, or 0.78, say they aren't a gamer. And then here, so if they don't play video games, in a theoretical ideal world, hopefully none of them call themselves a gamer if they don't play games. I know that's not reality for everybody. And then 100% would not call themselves a gamer if they don't play games. So this would be my tree diagram that I can use. So, oops, I need a little more room here. So what percent of all U.S. adults play video games and refer to themselves as a gamer? So play video games and refer to themselves as a gamer. So if I start here, play video games, so I need this probability, and call themselves a gamer, so I need this one. So I went down 2 branches. So multiplication rule says probability, they play video games and they call themselves a gamer. It's equal to 0.67 times 0.22. Plug that into a calculator unless you're good enough to do it in your head. I personally am not. 0.1474. So that's saying, according to this Pew Research poll, roughly 14.74% of all U.S. adults play video games and call themselves a gamer. Independent events. So this one can be a little tricky. I'll definitely post later. I have a set of examples talking about independent and disjoint. So some events, the idea is, well, event 1 doesn't have any effect on event B. But it's not just that, it's event A happening. Like if you know event A happened, it doesn't impact the probability like that event B happened. It doesn't necessarily cause a change in B. So suppose I roll 2 dice in a game. What is the probability I roll 2 6s? So if I roll it on roll 1, I can roll, there's one way to do that. Out of 36 goes, so 1 out of 36. Suppose I rolled 2 6s on my first roll, and now I'm going to roll again. So what's the probability that I roll 2 6s again? Well, here we consider rolling dice to be independent events, that whatever happened on the first roll, it doesn't have any impact on what's going on in the second roll. So it's still going to be 1 over 36. So knowing whatever happened on my first roll doesn't have any impact on how likely it is that I'll get 2 6s on my second roll. So then, oops, what is the outcome of the So is the outcome? Yes, it is. Because unless you're doing something really funny with your dice, roll 1 and roll 2 shouldn't have anything really to do with each other. So 2 events, and here's this big old technical, they're said to be independent if the likelihood of one event occurring is not influenced by the other event occurring. So we have this definition, they're independent if and only if you can say the probability of A, given that you know B happened, is just the probability of A. So knowing B happened did not impact the probability that A happened. Or the other way around, so the probability B happened, given you know that event A happened, is just probability B. So knowing that event A happened had no effect on the probability of event B happening. And we'll use some examples. What is really great is when we know that we have independent events, we can use this product rule. So if and only if, super, super important, if A and B are independent, the probability that A happens and the probability of B happens is just probability of A times the probability of B. But it's really important, you can only do this if they're independent. You should check to see if they're independent first. We almost always will throw something like this at y'all at one point. And it can be, so in this case, A and B, if A and B are 2 independent events, it's the product of 2 probabilities. If I had 3 of them, it would be 3 probabilities. Or if I had K of them, it would be K products. So for example, Monopoly, I have my buddy AJ loves Monopoly. I don't know how, but they manage to roll doubles suspiciously often. And in the game of Monopoly, if you roll doubles, you actually get to get another turn. So they'll roll doubles, they'll go again, and they'll get doubles again, and very suspicious. But however, if you roll doubles 3 times in a row, you go to jail. So what is the probability a player will roll 3 doubles in a row? So this is going to be, thanks to that multiplication rule, we can say it's probability doubles on firsts and doubles on seconds and doubles on third. I can rewrite that just as probability doubles times probability doubles times probability doubles. So throwback, remember there are 6 ways to get doubles out of 36 different, so just 6 out of 36, it's equal to 1/6. So I'll get 1/6 times 1/6 times 1/6. I'll actually get 1/216. It's small, let me double check. It's going to be something like 0.0046, and it goes on, but make sure you round appropriately. The next number is a 2, so it doesn't round up. So it looks like there's less than 1% probability if you're just truly like just rolling random rolls that you'd get doubles 3 times in a row, less than 1% of the time. So 0.46%. It's pretty small, a little less than 0.5%, half of 1%. So then, just to illustrate what I mean here about independence, I like this particular example. I mean, sorry about we like cards and coins way too much. So I have a standard deck of cards. For anybody not familiar, it has 52 cards in a deck. 52 weeks in a year. 4 seasons, right? 4 deck. Yeah, so suppose my friend Yuri, they're interested in the event of drawing an ace card on their second draw. So they're going to draw a first card and then they're going to draw a second card. and the deck has 4 ace cards. So they're cards that just have just one, whatever it is on their card. So I'm going to have A is the event where the first draw is an ace, and B is the probability that the second draw is an ace. So I'm going to have 2 scenarios, scenario A and, well, scenario 1 and scenario 2. So in scenario 1, Yuri replaces the first card into the deck and draws again. Are the events A and B independent? So probability that B happens, given that we know that A happens. So means probability that we get an ace on our second draw, given that we got an ace on our first draw. However, we get an ace on our first draw, put it back in the deck, shuffle, and then draw again. So here, we're going to have 4 aces we could pick from out of 52 cards. So it's just going to be 1/13. Off the top of my head, I don't know what that is. It's smaller than 10%. But it's totally dependent on the fact that we replaced the card. So then, and we could even rewrite it. So yeah. Probability that B happens given we drew anything besides an ace on the first one. So let's say I draw a card and I get a 3. I look at it, that's cool. I put it back in the deck, shuffle. There are still 4 aces in the deck. And there are 52 cards. So still 1/13. Because knowing that what happened in the first draw has no impact whatsoever on the second draw, I can say A and B are independent. Because here, probability B, probability of drawing an ace, that's just going to be 4 out of 52, which is 1/13. So scenario 2 is a little trickier though. So suppose that Yuri does not replace the first card. So, first one, so first card is ace. So probability that the second one is an ace, given the first one's an ace. So here, remember, we're not putting it back. So if the first card is an ace, that means now there's only 3 aces in the deck. And there aren't 52 cards anymore. There are 51. So my second scenario, first card is anything else. So anything that isn't an ace. The probability be given that we don't get an ace in the first. So remember, we're still keeping that first card. So suppose I draw from the deck and I get a 3. I don't put that 3 back in the deck. There are 51 cards left. Out of those 51 cards, 4 of them still are going to be aces. Well, these don't match anymore. So if somebody told me that if I'm using the method where I draw a card and I don't put it back in, what I got on the first draw absolutely matters. If it's an ace, that means I'm less likely to get an ace. There are fewer of them on my second draw. If I drew anything besides an ace, I still have 4 aces I can get. It's a higher probability. So knowing what happened in the first draw changes our perception of like, oh, well, no, that probability is higher if I know that this is the case. So first one, if you use replacement every time, those are independent events. If you don't have replacement, not independent. So that's it for lesson 15. We'll see you for 16.